This video shows the creation of a Kalman filter for a 1D system. Specifically, it's the system where we had a train car moving along a track. And the position of the train car is measured with a radio system. So we've got the distance from this tower to an antenna on the train, and we'll denote that with the variable x. And the train is moving with some velocity, x dot. Now, so we'll define our state as vector r, and it's made up of the coordinate x and its time derivative x dot. Okay. So when we're making the Kalman filter, we need to first write our process and measurement equations, so those models. So here's our process equations. Here are our process equations. So we've got the state at the current time, so r of k, and we'll look at each component. So the position at the current time is equal to the previous position. So this is a discrete equation. We're looking at positions at discrete points in time. So from one time step to the next, xk minus 1, xk. So the current position is the previous position plus the previous velocity, x dot k minus 1, multiplied by the time between intervals, k minus, anyway, delta t. And then, oh, I forgot to mention the driver of the train has input f, so he can put some force, and that's either an acceleration force, so that would be positive f, or it's a braking force, and that would be a negative value. And so here that force can affect our position, and so the acceleration is the force divided by the mass of the train. So we've got 1/2 times f divided by m, mass of the train, times delta t squared. So there's our equation for the position at time k. And now the velocity at time k is just the previous velocity, x dot at k minus 1, plus the acceleration f over m times delta t. And in order to use the Kalman equations, we'll need to write these in matrix form. So this is actually incomplete because I left off the error term, so the error vector. So plus v 1 k minus 1 plus v2 k minus 1. So v1 and v2 just refer to the fact that v is also a vector, so it's got so v is equal to v1 and v2. So here we've got v1 and v2. So rewriting this in matrix form, we have the state vector at r of k, or I'm sorry, the state at time k, which is equal to x of k and x dot k. So that's equal to a matrix F times the state at time k minus 1. So that's 1, delta t, 0, and 1. So we multiply that by the state at k minus 1. And then now we have input matrix B times the input. So all these matrices are just coming from these two equations here. And our input is the force F, so that's a scalar. And then plus V, K. So plus our error term at time K. So there's our process equation in matrix form. And this is equal to, so R of K is equal to F times R k minus 1 plus B times U of K plus right? So now we know what the matrix F is and the matrix B. And now we have the measurement model. And this is pretty straightforward. So our measurement, we denote with the vector z. So z at time k is equal to, so in this case it's just going to be the distance from here to here. We're going to say we'll measure that directly. So it's equal to x of k. And then there's going to be some error in that, so plus w of k. And so this is equal to the matrix H times the state vector R plus W K. So that looks like okay, so the transformation matrix is just 1, 0, and then our state vector here is x of k and x dot k, and then plus w of k. So there is h. So now we know f, b, and h. And so in order to perform the iterative process using the Kalman filter, we need all these matrices. So we need F, B, H, Q, R, X hat 0, 0. So our initial estimate and our initial estimate of our error covariance, P 0, 0. So we've already got F, B, and H. Q and R are the covariance matrices associated with V and W, respectively. And now I've stated that the Kalman filter provides an optimal estimate, and that's true if you know Q and R. So we don't know them exactly, and so we can just make up some values, and the Kalman filter will still provide a good estimate, a good fusion of the two models, the measurement and the process model, but it won't be an optimal estimate. So Q relates to our process equation. So we could assume that we know, we have a pretty good idea of the process. And so we could let Q be the identity matrix, and then say that our measurements are noisier. So then we could say R is equal to 5 times the identity matrix. Now ideally Q and R would come from some either error model analysis or measurements and statistical analysis of measurements. But in this case we're just going to make up these values for Q and R. And then our initial position, our initial estimate for the position, so in this case we want R. It's kind of confusing talking about because typically we write the state variable as X, but in this example I called it R. So our initial estimate for the state at time 0, we'll just say that initially the position of the train was 0 and the velocity was 10 meters per second. Or I'm sorry, just 10, because we don't have units. And then P, we'll just let this also be the identity matrix. And so from this point we could go ahead and begin using the Kalman filter. So at the next time, so we want to get our estimate for the state at time 1 just using the process model. So this is the prediction. Really all the work now is done for the Kalman filter. So we've got everything we need to let it run. As long as we're getting new measurements, Z, then we'll be good to go. I'll just go ahead and illustrate a little bit of it for you, just so we can get an idea of what to do with all these matrices. So here's our prediction step, and this comes from the prediction equation. So that's equal to F times our previous estimate, so R hat 0, 0, plus B times U. U of K. And we could just say, for example, let U of K equal 0.5. So we'll say there's a constant acceleration force going on in this example. Okay, so this is equal to 1, oh, and then delta T, we could say that's 0.05 seconds. So 1.0501. So there's our matrix F. And then now our previous state estimate, so 0 and 10. And then B, and the mass of the train, we'll say it's 500 kilograms. And this is, I should make this something bigger. So we'll say this is 50 newtons. It's not very much. Where were we? Okay, so now we've got F times our previous state estimate. Now we have the B matrix, so here's the B matrix, delta T squared over 2m. So 0.05 squared divided by 1,000. And then the second row is 0.05 divided by 500. And then multiply that by 50. So this will give us our prediction. Maybe I can do this. So this first row is going to be 0.5 plus well, I don't know what this is, 0.0. So this is 0.000125. So this force isn't very much to accelerate the train, especially in that little time. Okay, and then for the next row we've got 10 plus I guess 0.5. So our predicted position is 0.500125, and our predicted velocity is 10.5, I believe. Nope. This is 0.005. Okay, so 10 point. So there's our predicted position, and there's our predicted velocity. So we predict we're at half a meter, and our velocity is 10.005 meters per second. And then our predicted error covariance just comes from the prediction measure equation. So F times P00 F transpose plus Q. And so this is 1.0501 times the identity matrix times F transpose. And we said that Q was the identity matrix also. Oops. Okay, so there's the identity matrix Q. Like I said, we're going to stop there with working through the equations. Because like I said, all the work comes in determining what the matrices need to be, F, B, Q, H, R, and then our initial estimates, the state estimate at time 0 and the error covariance estimate at time 0.